Hi everyone, welcome to Maths World UK. My name is James Grime and today I am speaking with Paul Shafer. Paul is a mathematician from the University of Leeds and today Paul is going to talk to us about whether computers can do maths. One of the great questions in mathematics. In fact, this is a question that was actually solved by a young Alan Turing, who you may have heard of before. Alan Turing is a very famous British mathematician. Particularly, he's famous for his work as a codebreaker in World War II. But before World War II, Alan Turing decided to take on one of the great unsolved problems in maths at that time, which was called the decision problem. So today, Paul is going to explain what the decision problem was and how Alan Turing solved it and how his solution led to our modern world of computing today. Now, this problem was a very hard problem at the time, and the solution does involve some high-level maths. So don't worry if you don't follow everything, that is absolutely fine. But if you get the gist of the idea, then you're doing pretty well. But this kind of mathematics is what Paul studies. It's called mathematical logic. So I started my conversation with Paul by asking him to explain what is mathematical logic.
Geometry is the mathematics of shapes, maybe, and calculus is the mathematics of rates of change. We in logic like to say sometimes that mathematical logic is the mathematics of mathematics.
Which I love. I love that sort of thing. So you're looking at the fundamentals of maths itself.
Yes, you could say so, yes. The foundations of mathematics, some people also say.
Yeah, so tell us a little bit about that. So you're looking at how theorems and proofs are built up?
That's part of it, yes. A big part of it is what is actually provable and what is not provable. And related to that is what can computers do and what can computers not do? Like what can be computed and what can't be computed.
Well, I think you've set me up here because I believe that is something we're going to be talking about today. So I'll pass it over to you. What are we talking about today?
Can computers do mathematics? And I think this is a familiar question to mathematics students, right? Asked by their friends and family, why are you studying mathematics? Can't computers do everything already? And well, yeah, computers can do a lot. Yeah, of course, computers can do mathematics, right? Computers are great at mathematics. Right? Everybody has familiarity with this, right? They can make all sorts of numerical calculations and approximations. As I have sort of a few silly ones written down here. And they can do fancier stuff than that even. They can make symbolic calculations. And nowadays they're even very good at doing symbolic calculus, right? Figure out derivatives and antiderivatives of all sorts of functions. And nowadays, there's even these proof assistants, and computers can help mathematicians even develop new mathematical proofs. But they can't do everything. What computers have trouble with is, in general, determining what sort of mathematical statements are true and what sort of mathematical statements are false. So what I want to talk about today is that computers cannot solve the so-called decision problem, which was formulated by David Hilbert and Willem Ackermann in the 30s. And that this decision problem could not be solved by computers was proved by, two mathematicians independently, very closely around the same time. One, Alonzo Church in the US, and then we're going to talk about today also Turing in the UK. So the problem is you or someone, say, is given a mathematical statement, and what you're supposed to determine is that statement true, always true, no matter how you interpret the statement? If you want to know whether or not this statement like this or this particular statement are true or false, you have to say what all the symbols mean, right? You have to say, well, what are these x's that the variables range over? And what do the properties A, B, and C mean, right? Once somebody tells you that, right, tells you how to interpret the statement, then you can decide whether it's true or false. Okay, so on the next slide here, I have another sort of simpler statement just to give an example of how you can interpret the statement in two different ways, right? For this particular statement, for every x, if x has property E, then that x has property P, right? We're going to come up with two different interpretations of this statement, one to make it true and one to make it false. Because if I think of E as saying x is even and P as saying x is any number, then the statement just says, for every x, if x is an even number, then it's a number, okay, which is of course true. So what if I want to make this statement false? Now p of x is going to mean x is an odd number. So if I change the meaning of the symbol that way, then all of a sudden this statement says something very silly, right? It now says every even number is an odd number, right? Because we changed the meaning of p to mean that x is an odd number, right? And that's of course false, right? That's sort of as false as possible, right? No even number is an odd number. Okay, so if I change the interpretation just of this one symbol in this case, then I've changed my statement from a true statement to a false statement. Okay, but the point here is that if you're faced with any mathematical statement, whether it's true or false depends on how you interpret the symbols. Well, actually, sometimes a statement is going to be true no matter how you interpret the symbols, right? Just by sort of virtue of its logical structure, it's always going to be true. So here's a statement that is always going to be true no matter how I interpret the symbols. Right, so I have a little argument here of why this thing is true no matter what, but I'm sure people already see it, right? It says that, well, if every x already has property p, and everything that has property p has property q, then it must be that, well, everything has property q. Okay, and we didn't need to know anything specific about what x meant or what property p or property q actually was, right? We argued just completely abstractly that this is going to be true no matter what. And statements like this that are true no matter how you interpret the symbols are called logically valid. Right, and that's what the decision problem is. You're given a medical statement and you're supposed to determine whether or not it is logically valid. That's the problem. And what Turing showed is that there's no mechanical procedure for solving this this decision problem. Okay, nowadays we would phrase this as saying there's no computer program that takes as input a mathematical statement and gives you as output, yes, it is logically valid, or no, it's not logically valid. Okay, so Turing's idea was to invent these machines that are now called Turing machines. And he gave an argument saying that, just sort of a heuristic argument explaining why his machines were good machines, right? How they could replicate any sort of pen and paper calculation that a human could do following some collection of instructions. He developed what's called a universal Turing machine that can simulate any other Turing machine. So this universal machine can take as input sort of a code for another machine and then simulate what that machine does. Right. The way I like to think of this as that sort of like to think of Turing machines as not really as physical machines, but more as like a program language. And in that sort of line of thought, you would think of a universal machine as an operating system for Turing machines, right? You give it some program and then it does and that runs the program for you. So we didn't just show directly that there's no machine for solving the decision problem. He went through this other problem called the halting problem, which is now very famous in its own right, and maybe some of you have heard of it. So the halting problem is you're given a code for a computer program, or in this case, a Turing machine, and you're supposed to determine whether or not that program or machine is ever going to terminate, right? If you run a program, right, it runs and maybe it stops if it's a well-made program, or maybe there's some bugs and your program just runs forever without stopping. Okay, and the halting problem is to determine, whether you have a good program that stops or whether you have a bad program that doesn't. Okay, and Turing showed that no Turing machine can solve this halting problem, right? The Turing machine can't determine whether or not, in general, another machine is ever going to terminate, or nowadays, no computer program is going to be able, in general, to determine whether or not some other program is going to terminate. Okay, so we had this mechanical way of translating a machine into a statement in such a way that the machine terminates if and only if the statement that arises from it is logically valid. Okay, so this equates these two problems, the halting problem, which he already knew is not computable, And this decision problem, which he's trying to show, is is not computable. So if there were a machine to solve the decision problem, you could convert that into another machine that would solve the halting problem. Already know that there's no machine to solve the halting problem, and therefore there could not be in the first place any machine to solve the decision problem. So that was the idea of his argument. Okay, and let me finish with just one more thing, which is that this whole time the discussion has been pretty abstract, right? We've been talking about these very abstract mathematical statements with sort of symbols that you can interpret however you like, right? But what if that's not what you're interested in? What if you're interested in a particular mathematical structure and symbols with particular interpretation that you're already familiar with? So Turing's work also shows that it's not computable to determine whether or not the statement is true just of the natural numbers. And this is related to Gödel's incompleteness theorem, which says that no matter what proof system you set up for trying to determine what statements are true and false about the natural numbers, right? So long as this is a reasonable system in some ways, sort of meaning that you've set up your proof system in a way that the proofs can be mechanically checked, then there's always going to be statements that are true but not provable in your system.
When you talk about Turing machines, you're really talking about computers and things, and
yes,
mobile phones and things like that. So my mobile phone is a Turing machine.
Yeah.
And is that a universal Turing machine?
Sure. Yeah. I mean, it probably runs some kind of Java or whatever. Well, maybe not. But, I mean, it runs some industrial programming language, right?
So there was a difference between a Turing machine and a universal Turing machine. Would be like the Turing machines be like the individual apps on my phone, and then the phone itself
so the
is more
universal. Your universal Turing machine would be like the iPhone OS or the Android, right? The program that runs the other programs. That would be the universal Turing machine on your, and then all the apps are individual Turing machines, and you tell the operating system, I want to run the calculator machine or the whatever Instagram machine.
And so I guess sometimes my app might fail. So I guess is it true to say that the halting problem is like having an app that can tell me whether another app is going to fail or not?
Yes, that's right.
Yeah,
exactly.
And no such app exists.
No such app exists. It would be great if it did, right? Then you could just run an app to determine whether or not your other apps have bugs in them.
Right.
But can't be done in general.
Oh. Thanks, Paul. And I think one of the interesting things about this story to me is how really computers came out as an almost accidental, unintended consequence of Alan Turing's work, because Alan Turing wasn't trying to invent a computer. He was trying to solve a completely different problem, this high-level problem within maths itself. But to do that, he then conceived of this computing machine, which our whole modern world now depends. And I love that, and I think that is a really good case for staying curious, and I will see you next time.